Every skyscraper on Earth follows the same unwritten rule. It climbs toward the sky, floor after floor, steel above steel. For nearly 150 years, that's how humanity has measured ambition. But one city decided that wasn't enough. Instead of building another tower, its engineers attempted something no one had ever done before. They suspended an entire building, longer than 3 football fields, between 4 skyscrapers, nearly 1,000 feet above the ground. A structure weighing more than 12,000 tons. One miscalculation, one failed cable, one unexpected gust of wind could have turned one of the most ambitious engineering projects in history into one of its greatest disasters. So, why take that risk? And how did they make the impossible stay in the air? This is the incredible story of China's floating skyscraper. Before you can understand the building, you have to understand the city. Chongqing isn't like New York. It isn't like Dubai. And it certainly isn't like Chicago. Most modern cities spread outward. Chongqing couldn't. Instead, it grew upward and sideways. Home to more than 30 million people across its municipality, Chongqing is one of the world's largest urban regions. Yet its downtown core sits on steep hills where the mighty Yangtze and Jialing rivers meet. Instead of broad, flat streets, the landscape is carved into cliffs, ridges, and valleys. Entire neighborhoods exist on different elevations. A walk that looks like 5 minutes on a map might involve dozens of staircases and several elevators. Some apartment buildings have entrances on completely different floors, depending on which street you're standing on. It's one of the few places on Earth where a subway train can pass directly through a residential building. Not because engineers ran out of options, but because the terrain left them few alternatives. Here, gravity shapes daily life. Roads twist around mountains. Highways stack on top of one another. Bridges leap across deep river valleys. The city has become a global showcase of vertical urban planning. But by the early 2000s, another challenge emerged. The population kept growing. Businesses wanted premium office space. Luxury apartments were in demand. International companies wanted a landmark development unlike anything else in Asia. The obvious solution was to build taller, but Chongqing already had towers climbing hundreds of feet into the air. So, developers asked a different question. What if the next frontier wasn't higher, but smarter? What if separate skyscrapers could function as one connected city? That simple idea would soon evolve into one of the boldest architectural experiments of the 21st century. But first, someone had to imagine it. And the person who did wasn't trying to build the world's strangest skyscraper. He was trying to tell a story. When architect Moshe Safdie first studied Chongqing's skyline, he didn't see isolated towers. He saw a harbor. For decades, Safdie had become known for designing projects that blended architecture with public space, rather than treating buildings as separate objects. His goal wasn't simply to maximize height. It was to create places where people could live, work, and gather in entirely new ways. Standing where the Yangtze and Jialing rivers meet, he imagined the city's future as a fleet of ships arriving at the gateway to Western China. That vision became Raffles City Chongqing. 8 skyscrapers rising from a shared podium. Homes, hotels, offices, shopping, public gardens, transportation, all connected into one massive urban ecosystem. But one feature would redefine the entire project. A horizontal structure stretching across the tops of 4 towers. Known simply as the Crystal, it would span about 300 meters, roughly the length of 3 football fields. From a distance, it looks like a bridge, but it isn't. Inside are observation spaces, restaurants, gardens, event venues, mechanical systems, and public areas filled with natural light. It's essentially another building, just turned sideways. The design also served practical purposes. Connecting multiple towers allows people to move between them without returning to street level. Shared mechanical systems improve efficiency, while elevated public spaces create experiences impossible to build at ground level in such a crowded district. Still, the design immediately raised uncomfortable questions. Could 4 separate skyscrapers actually support a structure this enormous? Could something this long survive earthquakes? What happens when each tower sways differently in strong winds? And perhaps the biggest question of all, how do you even build it? Because while architects could draw almost anything, physics still had the final vote. As engineers soon discovered, the greatest challenge wasn't keeping the building in the air. It was keeping the ground underneath it from failing first. Most people admire skyscrapers by looking up. Engineers usually look down. Because no matter how spectacular a building appears, everything depends on what lies beneath it. The Raffles City site sat near the meeting point of 2 massive rivers. Over thousands of years, layers of sediment had accumulated beneath parts of the riverbank, creating ground conditions that demanded careful investigation before construction could begin. The solution wasn't simply to pour a thicker foundation. Crews drilled deep into stable bedrock below the surface, installing reinforced concrete piles capable of transferring enormous loads away from weaker soil above. Each pile became part of a vast underground support network, hidden from view, yet carrying millions of tons. Meanwhile, engineers had to account for another invisible threat: earthquakes. Although Chongqing isn't among China's highest seismic risk regions, modern high-rise construction must still withstand significant ground movement. That meant designing foundations that were both incredibly strong and flexible enough to absorb energy. Every column, every reinforced core, every connection had to work together as one integrated system. But solving the foundation only unlocked an even greater challenge. Because once the towers reached hundreds of feet into the air, gravity wasn't the only force trying to stop the project. The wind arrived, and suddenly, everything changed. It wasn't the weight that terrified engineers anymore. It was the sky itself. Imagine trying to carry a giant sheet of plywood during a windstorm. Now imagine that sheet weighs more than 12,000 tons. That's the problem engineers faced. The higher a building rises, the stronger the wind becomes. Air rushing between Chongqing's towers accelerates through narrow gaps, creating powerful gusts that can push against exposed steel with tremendous force. Originally, engineers explored conventional construction methods. Could cranes lift individual sections? Could workers assemble the structure piece by piece high above the city? On paper, it sounded reasonable. Reality disagreed. A partially completed skybridge would behave like an enormous sail. Before its structural frame was fully connected, wind could twist unfinished sections beyond safe limits. Even tiny movements at one end could become massive stresses across hundreds of feet of steel. Traditional tower cranes also faced practical limits. Not only would they need extraordinary lifting capacity, they would also require incredible reach and precision while operating hundreds of feet above one of China's busiest urban centers. The risk simply became too great. So engineers made an astonishing decision. They would build the entire structure somewhere far safer. Not in the clouds, not suspended between towers, but almost entirely at ground level. There, Workers could assemble huge steel sections under controlled conditions, where equipment was easier to access and weather posed far fewer hazards. It was a bold solution, but it created an even bigger problem. Once the structure was complete, how do you lift an entire building into the sky? Not a bridge segment, not a steel beam, an entire building, thousands of tons, hundreds of feet, with almost no room for error. The answer would push modern engineering to its absolute limit. And for several tense days, the whole world watched. By now, the engineering team had accepted one simple truth. If they couldn't safely build the structure in the sky, they would bring the sky down to the construction site. Instead of assembling the crystal hundreds of feet above the city, engineers transformed the roof of the massive retail podium into a temporary factory. Here, surrounded by cranes, welding stations, and precision measuring equipment, workers began constructing one of the largest steel structures ever assembled at ground level before being lifted into place. Every piece had to fit with extraordinary precision, not centimeters, not even millimeters. In many cases, tolerances were measured to fractions of a millimeter. Because when a structure stretches nearly 300 meters, or almost 1,000 feet, even the smallest error at one end can become inches of misalignment at the other. Before a single steel beam was installed, engineers created an incredibly detailed digital model of the entire structure. Using building information modeling, or BIM, every bolt, weld, pipe, electrical conduit, and ventilation system was mapped in 3 dimensions long before construction began. This virtual building allowed engineers to detect potential conflicts before they became expensive and dangerous mistakes. Then came the steel. Thousands of tons of high-strength structural steel arrived in carefully planned sequences. Massive curved trusses formed the backbone of the skybridge, designed not only to carry its own immense weight, but also to support restaurants, observation spaces, mechanical equipment, and thousands of visitors every day. Unlike an ordinary bridge, this structure would behave like an occupied building. It needed heating and cooling systems, fire protection, electrical infrastructure, elevators, water supply, emergency exits, everything found inside a modern high-rise. Even sections of the exterior glass facade were installed before the lift began, reducing the amount of dangerous high-altitude work later. As the months passed, what had started as scattered piles of steel slowly transformed into something astonishing. Lying horizontally across the construction platform sat an entire building, ready to fly. But assembling it was only half the challenge. The real test was lifting 12,000 tons without allowing one corner to move faster than another. Because if that happened, the entire structure could twist itself apart before ever reaching the sky.